right, AP Calculus, we're into test number 9 review. Let's go for number 6. Let R be the region bounded by these functions. Y equals x cubed plus 1, the x-axis, x equals 0, x equals 1. And we're going to revolve around the x-axis. So what's the first thing we do? Is we draw a picture. All right, you know what this guy looks like. That's y equals x cubed plus 1. And then we get the x-axis. You got x equals 0, which is the y-axis. And you got x equals 1 right here. So that's our region. R. Now we're going to rotate it around the x-axis, so we draw its reflection. And now everything will be an x dx. Everything. Okay, so our cuts will be in x, and we will get these discs, right? So we start again the volume of the disc, which is a cylinder, so that's pi r squared h. What's the height? dx. What's the height? I mean, what's the radius? Well, the radius is this thing right here, would you agree? So that radius is going to be like y2 minus y1, the top, y top minus y bottom. What's y top? X cubed plus 1. What's y bottom? Y equals 0. So this is just x cubed plus 1. Therefore, what we've got here is pi times x cubed plus 1 squared dx. Now we want to get the volume of the shape. So the volume of the shape is this volume of the disk.
If you don't want to really download anything,
all the disks. You're going to sum up the volumes of all the disks from x equals something to x equals something. X equals 0 to x equals 1. Okay, so that should get the job done. Now, of course, you have to FOIL and then anti-differentiate. Use the first part of the fundamental theorem to evaluate that. If you do, you are going to get the following. You are going to get 23 pi over 14. And now what are the units over here? Well, this is a measure of volume. Volume is cubic, so cubic units. Number 7 says, find the slope of the tangent to the graph of y equals 3 x squared plus 1 plus natural log of x cubed plus 1 at the point 0, 3. All right, so they're asking you to eventually get the slope of the tangent line. It's the derivative, right? dy dx at 0, 3. So here we go. dy dx is going to equal. Well, we got to know how to anti-differentiate 3 to the x squared plus 1. 3 to the x squared plus 1 is very similar to e to the x squared plus 1, right? If it was e to the x squared plus 1, it would be like composite, 3 to the x squared plus 1 times the derivative of the inner, which is 2x, right? But it's not e to the x, it's 3 to the x. There's that little add-on. Do you remember what the little add-on is? It's the add-on of natural log of 3. So we're taking the derivative of the outer, we're taking the derivative of 3 to the x, right? It's 3 to the x, natural log of 3. You got to take that into consideration. And this is just chain rule, right? 1 over x cubed plus 1 times 3x squared. Good. Now, all you have to do is plug in this order pair 0, 3, so you get dy dx is equal to 3 to the 0 plus 1 times 2 times 0, natural log of 3 plus 1 over 0 cubed plus 1 times 3 times 0, which clearly equals 0. Okay. Number 8 is going to have us do integrate x e to the 2x. No problem. You know it's u substitution. So let's go with u equals x, and we'll go with dv equaling e to the 2x dx. It's as good a guess as any. Differentiate here, and you get du dx is equal to 1. Make this dv dx equals e to the 2x and anti-differentiate, so you get b is equal to, it's something like e to the 2x, but if I differentiate e to the 2x, I'd get 2 e to the 2x, so this must be like 1/2 e to the 2x. All right, so now I have all my components. X, this is du equals dx, so I've got the du component, got the dv component, and I got the v component. All right, so now it's u, v, minus the integral of v du. And this is an easy integral, right? So let's integrate it. We get x, this is 1/2, this is 1/2 x, e to the 2x, and then here, if we anti-differentiate e to the 2x, we get 1/2, this is minus 1/4 e to the 2x plus c. Let's see if that's right. Take derivative here, you get 1/2 e to the 2x. Perfect. That should be your answer then. All right, and the answer they have here looks to be exactly the same. Now you certainly could factor out 1/2 e to the x if you wanted to, 1/2 e to the 2x if you wanted to, but there really is no need. Number 9, you're like, oh man, what is this? I don't know what this is. This is a gimmick. And remember, there are some simple algebra moves you could do. This breaks into x over the square roots of x minus 2 over the square roots of x dx, right? So this is then just the square roots of x minus 2x to the negative 1/2 dx. So you just rearranged it, then taking the antiderivative is not hard at all. Anti-differentiate x to the 1/2, and you get 2/3 x to the 3/2, right? If you differentiated this, you'd get x to the 1/2 minus, this becomes, this will be x to the 1/2, so it's over 2, so this should just be x to the 1/2. Let's test that out. 1/2 x to the negative 1/2. Oh, that's not what we want. So this is 4x, let's see, that would get me 2x to the negative 1/2. Correct, plus c. So let's just check that, make sure it's the right answer. 2 is x minus 4x 1/2 plus c. Good. Number 10 tells us, given this function right here, find the critical numbers. Well, you know how to find critical numbers. You get the zeros, or the places where, you get the critical numbers, you get the zeros of the first derivative where the first derivative doesn't exist. So let's just differentiate. G prime of x equals, you must see this as a product of these two functions. And then within the second function, you got a composite function. So first times the derivative of the second plus the second times the derivative of the first. Well, first times derivative of the second, so that's this chain rule in here. So we're going to get derivative of the outer with respect to the inner times the derivative of the inner. All right, so you had product rule with a chain rule inside. Let's clean this up a little. We get 3 natural log of x squared plus natural log of x cubed. You got addends, not very easy to solve for the zeros. All right, we're getting zeros or d and e of addends, but it's certainly easy to do for multiplicand, so factor out the highest common factor here, which is natural log of x squared, and that's going to be 3 plus natural log of x. Break this up. 0 equals natural log of x squared, where 0 is equal to 3 plus natural log of x. Well, to undo the square function, plus or minus the square root of 0 is 0. 0 equals natural log of x, therefore what? X must equal 1. Over here, bring the negative 3 to the other side, apply exponential base e to both sides. I'll show that to you real quick. So you got negative 3 equals natural log of x. How do you undo the natural log function? Exponential base e. That's like exponential base e to both sides. These cancel, and you get down to x equals e to the negative 3, which is 1 over e to the third. So these are our two critical numbers, x equals 1 and x equals 1 over e to the third. This problem right here, number 11, you probably first instinct, because you've been working with it, is reduction of odd powers, right, of trigonometric functions. But before you do anything crazy like that, which you probably won't even have to do on the AP exam, you should just look at this as a plain old use substitution. How do you do substitution problems? You find a composite function, you say what's the inner function, in this case cosine of x. Is its derivative also in the integrand? Yeah, so we're good to go. U is equal to cosine of x. Before I finish this, let's just rewrite this. Do you know that cosine cubed x is the same as, cosine cubed x is the same as cosine of x cubed? You have to see it that way. You have to see the outer function of the cube function here. All right, du dx is equal to negative sine of x. We want sine of x dx on the right-hand side here. So we got negative du. All right, therefore, sine of x dx becomes negative du, and cosine cubed x is u cubed. And if you differentiate, you get negative 1/4 u to the 4th plus c, which is equal to negative 1/4 times cosine of x to the 4th plus c, which most of you will probably write as negative 1/4 cosine 4th of x plus c. Let's check that out, make sure it's correct. Yep, that's what's here on the key. Last problem, find the maximum area of the embedded rectangle. All right, drawing a picture is super important. And then using common sense. What am I maximizing? Area of a rectangle. So whatever I'm maximizing in an optimization problem, that's what I got to find a function for. Well, start basic. What's the area of this rectangle going to be? It's area of any rectangle is base times height. Now, be very, very specific. I want to get it in terms of a of x, right? What is this right here? What's this distance right here? By definition, it is what? X. Doesn't x come y mean go over x up y? So what's this height right here? It is y. Okay, so now let's rewrite this thing. A of x, a is a function of x as opposed to a function of b, h, is got a base. Now look at the whole base. See the whole base right here? How many x's is that? How many x's in that whole base? It's just one x? No, it's two x's. There's an x here and an equivalent sized x over there. So that's 2x. And what's the height? Y. That's important that you get the right initial function. It's not very hard. Then, how do you finish an optimization problem? In theory, you would differentiate, get the critical numbers and endpoints, and then test them to see which one produces the maximum area. But we don't like 3 variables. We like 2 variables. Which variable you want to get rid of? Y? Okay, no problem. 2x, where can you get this y from? Well, it's right here. It's that defined function, isn't it? That's that height right there. Okay, so that's 4 minus x squared. Or, you got 8x. Was that x squared or x? Maybe I wrote on this problem wrong. Number 12, I think I remember being to the 4th. It was to the 4th. So then this is 4 minus x to the 4th, which is minus 2x to the 5th. Okay, so that's my area function, independent variable x, dependent variable a of x. I'm going to take its derivative and find the critical numbers. So a prime of x is equal to 8 minus 10x to the 4th. I'm going to set that equal to 0 and solve. So that means x is going to equal, bring 8 to the other side. That's like 4/5. Take the 4th root. So this is the 4th root of 4/5. That's my critical number. Now in theory, what I'm going to do is test endpoints and critical numbers if I use the absolute extrema test, which is theoretically what any optimization problem is. But if I want, I could just use the first derivative test. It's really up to you. Just make sure you, culturally, both will probably be accepted. I'm going to use the absolute extrema test. How do you do that again? You have to test 2 things, critical numbers and endpoints. So you have x and a of x, the thing you're maximizing. There should be one endpoint, there should be one critical number right here, and there should be another endpoint. So what was our critical number? It was 4/5 to the 1/4 power. All right, 4/5 to the 1/4 power. But what are our endpoints? What do you mean endpoints? The limitations on the domain. Obviously, the domain here, it's all real numbers mathematically, but that doesn't make any sense here. What can x actually vary over? X could be as small, if you compress this into a tall, thin rectangle, your x could be as small as 0. And if you kind of stretched it this way and embedded it this way, then x could be as long as that distance. Like this distance right here? Well, what distance is that? Like, what exact distance would that be? What actual number distance would that be? Wait, how are you going to find it? Well, finding the 0 right here. If you find that 0, then you know. Well, clearly, what's the 0? What's the 0 of this function right here? What is it? Fourth root of 2? Is that right?
So, Alex,
Square root of 2. No, it's a square root of 2.
give me a second.
Right? Square root of 2 squared would be 2, and that squared would be 4. 4 minus 4 equals 0. So the 0 is square root of 2 comma 0. Would you agree? Good. So that's the maximum x could ever be. When you try to bounds for x, it could be as small as 0 as big as that. So square roots of 2. Now,
I'm not dealing with GitHub right now. I'm just gonna.
it's obvious that if you take this rectangle and you allow x to get as big as you want, then you're just going to get basically your rectangle is going to look like this. That's it. That'll be a whole rectangle, and it'll have an area of 0. Likewise, if you let x go to 0, then you're basically going to get this rectangle, which has as much height as it can, but has no x, so it's got an area of 0. So those are dumb choices. So the answer is clearly whatever's going to come out of the critical number. That's always the case in these problems, which is why you could actually use the first derivative test if you want, because it's almost considered common sense that the endpoints don't have any chance of being the max here, right? If you use the first derivative test, you're going to have to test to the left and the right of the critical number on a sign chart, like you do in the first derivative test, just to prove that you're going from a positive to a negative derivative, or increasing to decreasing to have a max. But I'm going to finish the absolute extrema test, where I test my endpoints and my critical numbers. So how do I test a critical number? I just stick it back into the thing I'm maximizing to find out the maximum area. So I'm just stick it right here. So area is going to equal 8 times, what was my critical number? The 4th root of 4/5 minus 2 times the 4th root of 4/5 to the 5th.
Okay, guys, I have a new task for you, and you're gonna hate it.
This looks disgusting, and I guess on some level it is, but it is the area, whatever it is. And that's that area. And what would the units be?
Oh, because this thing.
Square units, because we're maximizing area. So that should be your answer then. Yeah.
Right, guys. So we're gonna have to rename all the files to kind of tell us who